So we have an object stays at rest, object at rest, wants to stay at rest, object in motion stays in motion, force gauge is going to change. If you change a mass 1 kilogram and exert an acceleration of 1 meter per second squared, we're going to get 1 newton. So a newton, or 1 N, all right, we call it just a newton, is equivalent to a kilogram meter per second squared. So picture like a book, and you move it faster and faster. You accelerate it. All right, that is a force. Because coming back to the idea that we have to make motion and it has to increase in speed. A car coasting on the road at 55 miles an hour forever and ever and ever has no force on it because it's not going any faster or any slower. Now in the real world, the car slows down because the wind against the windshield is a force, and that slows our motion down. Again, the best example is space, right? If you get going at a certain speed in space, it's a vacuum, there's no air friction, there's nothing lost, we keep going. So when something has a constant velocity in space, there is no force. You fire the rockets, right, and then you go. Once you shut the rockets off, you're at that speed. Does anybody have any clue at all what a newton is? I mean, we know what a pound is, right? We all have our weight. What's a newton? 1 kilogram at 1 meter per second squared. You guys ever hold an apple? An apple in your hand, a regular size, old delicious apple, is about 1 newton of weight. When you hold it out in your hand, you're basically holding 1 newton of force. All right? Not like a crab apple, that's probably half a newton. But again, it just gives you a feel. This is about 1 apple for weight. Okay? An apple. I suppose it could have been a different fruit, but I like apples. All right? So you get a feel for what it is. All right. When you look at the force, and this is a force, guys. This is how we're going to measure it. It comes down to mass matters. All right. This leads us into our second rule. Okay. If I drop a bowling ball or a marble on your toe, it matters which one it is, right? Because the bowling ball weighs probably 10 kilograms, right? The round numbers, keep to round them up. The marble probably doesn't even weigh 0.005 kilograms, all right? So every time we do something, and that comes down to, it's a direct relationship, isn't it? Think about it. The bigger the mass here, the more force you'll have over here, assuming that the acceleration is the same, okay? So mass matters. And when we talk about an object, all right, like a bowling ball, like a marble, and this is the example I gave, we have to define it. And it's simply defined by something we have termed momentum, all right? It's a part of the force. Momentum is part force. And the longer you let the bowling ball fall, right, the more it hurts. And what I mean by that is if you drop it like 1 inch over your foot, if it just slips onto your foot, does that hurt? A little bit, but not too bad, right? What if you drop it from like 12 inches off your foot? That hurts. What if you drop it from like 8 feet or 6 feet off your foot? If there's a hospital visit, right? You break a bone, most likely, in your toe, right? Unless you have steel-toed shoes, right?
They bend down and cut your toes off.
All right. Now, what's the difference? As you go up, does the mass change as you move the bowling ball up? It's always 10 kilograms, right? So we agree the mass does not change. The velocity changes. How long we let it fall, Earth accelerates it, the velocity changes. So momentum, and it has, since it's velocity, it has vectors. Momentum is mass times velocity. Now, we got to catch, this is not a newton for a unit. If we look at the unit that are going to happen here, this is not a newton. This is not a force, this is a momentum. All right? So if I drop a bowling ball at 10 kilograms and a marble, and we'll call it 5 grams, or 0.005 kilograms. And if I allow it to drop I don't know, for about a second, all right, it's going to be going roughly 10 meters per second, all right? The momentum here is 10 kilograms times 10 meters per second down. So I get 100 kilogram meter seconds, and there is no better unit for the momentum. Now let's be clear, we're dropping that bowling ball from about, it's going to fall a full second. We're dropping from like 18 feet high. That's going to probably leave a big hole in the floor, right? Definitely wouldn't want to do it in your house. It would definitely break a wood floor. The marble, per se, would not be such a big deal. And again, it's down. It's going to have the same speed. We just... This is momentum, guys. Momentum is simply a mass times a velocity. And we realize that the bigger the mass, the more force it will have, okay? The larger the velocity, as the velocity increases, what makes velocity increase? Height, acceleration, right? As we go up, the acceleration of gravity. So again, this is momentum, and it's buried in everything we do. So remember how I said Chapter 4 leads to Chapter 5? We won't talk about momentum very much after we get to Chapter 5. We'll always talk about force. But this is part of force. So one of your homework problems was slapping a piece of clay against the wall, right? I know, it was ages ago. That's why I wanted to call it up. So long ago, in 29. A 1 kilogram wad of clay is slammed it straight into a wall at a speed of 10 meters per second. If the clay sticks in place, what was the impulse that acted on it via the wall? Now, impulse is the change in momentum. All right, I should find that before we talk about this. So when we talk about this, mass matters. We have a momentum. Impulse is just a measure of momentum, all right? It's just... So let's talk about that clay. We're going to slap a 1 kilogram piece of clay that was traveling 10 meters per second up against the wall, is what it said. Can you picture this problem here? Here's a wall. Here's a lob of clay. We throw it into the wall. Right? That's initial condition, right? The initial condition here. What's it going to look like after it hits the wall? Do you guys agree it'll look something like this? The mass does not change, right? But what happens to the velocity once it's all done? It's zero. Stop. Right? Does everybody agree that the velocity now is 0 meters per second? So, if impulse is a change in momentum, initially this had a momentum of 10, right? Just P equals mass times velocity. 10 kilograms per meter per second to the right. And what's the momentum after it's stuck to the wall? 0. Guys, the velocity is 0. All the energy is gone. It's gone somewhere else. It's not in the clay anymore. Good point. It's never destroyed. That's probably a bad way to say it. You're right. Everybody, there's no momentum. So what's the change in momentum for this problem? It's negative 10 kilograms per second. Because it was traveling 10 kilograms per meter second to the right, the change then is just the final state minus the initial state. It is not anything amazing. We should just realize that, and I agree, negative 10 meters per second to the right, or you could say the impulse was 10 meters per second, 10 kilogram meter per second to the left, right? Vector analysis. Mass matters though. The heavier, if you make the clay larger, Impulse will go up because the momentum will go up. If you throw the clay harder, you increase the velocity. All right? That would make the momentum go up. All right? And again, the way you make velocity go up, you heard I said throw it harder, right? That is a force. That is the agent of change. Something has to act on it. Otherwise, what does that 1 kilogram blob of clay want to do? It just wants to sit on the desk. Right? It doesn't want to move anywhere. And once you put it in motion, it doesn't want to do anything until it hits the wall again. And that wall becomes the agent of change. All right? Boom. This is impulse. So, if on your note sheet you got momentum, I know that impulse, all right, in your book it's defined. I'll use the right letters. It doesn't even have a symbol. All right. You can do it a couple ways. You can say it's the momentum final minus the momentum initial, which is the way I learned long ago in engineering. All right. And then we know that momentum is mass times velocity. All right. So those are the equations. And again, I will not ask you anything tricky. I won't make you throw it on an angle. All right. I won't, because those things really don't help us understand physics. So we have these two equations. And this is momentum. And this does have a symbol. And someone's going to ask me, why is it P? I don't know. It just always is. I think because M is for mass. How about that? I don't know why it's P. It just is. Yeah. All right. So we have these two equations. Now, instead of going through the proof, which would kill me, all right, the other thing we can do is, since this is change of momentum, we can put this in terms of time. So before we do that, I said mass matters. Everybody understands that, right? We get the idea that a marble and one ball hurt differently, right, when we drop them on our toe. What about force and time? All right? What's the relationship there? Now, I'll tell you what, guys. I can only push so hard. I can only push with so much force. I can only put 20, 30 pounds worth of force onto something. All right? If I'm moving something, how many guys have ever pushed a car that's stalled out or an object? Has everybody tried that before? Or something where you start pushing and it's really hard at first, but then as you push, what happens? It's easier and easier and easier. You guys, right? And that's a symptom of you guys are only able to push with so much force for an instant. The more time you push in, the more force you put in as an agent of change. As you increase the time, all right, you can get it going. So think about pushing a car. You start pushing the car, and you push pretty hard, right? But I'll pick on Ryan. Ryan, what do you think you can push with if you really push hard? 100 pounds? 100 pounds of force. So Ryan pushes hard with 100 pounds, okay? And he'll push for 10 seconds, and now get it going. Is there a way for us to do that differently? If we want to make the car roll? More force and less time. What if I go get my car? Have you ever done this? Right? Go get my car, put it in drive, come up behind, touch the bumpers, and just hit the old gas pedal. Right? And what happens? Man, oh man. All of a sudden, and what's the thing you're careful of? You ever done this? You don't want to go too fast, and you don't want to get a gap and then hit him again. All right? If you ever pulled anybody with a chain, you don't want the chain to get loose. You guys are all kind of thinking this is a joke, but think about this is exactly, when we talk about force and time, this is exactly how it works. I could have Ryan push, and he could spin all day, or I can get behind and push, and I will impart 1,000 pounds for just 1 second, where Ryan has to impart 100 pounds for 10 seconds. And there is a direct relationship between the amount of force and the amount of time and the amount of motion that occurs. All right, and we're going to talk about that homework. I will not put this on a test, and I don't know where that puts you guys. I will not make you know this for a test, ever. All right? This is impulse, delta P, right? The change in momentum is impulse. And if you take the impulse divided by the time, they're going to tell you it equals the average force. Well, force and time then, if you multiply this, all right, by delta t on both sides, here's what I want you to see. That the momentum, or the impulse, the change in momentum, is proportional to the force, and it's proportional to the time. What I mean by that is if I increase the force here, that increases the momentum. Does everybody agree? Or if I increase the time, it increases the force. So let's do it in SI, all right? Let's do it in this. So we're going to, man, oh man, you're a weak man now, because I'm going to only make you push 100 newtons worth of force, okay, Ryan? So that means you can only push 100 apples around. Okay. Huh? What if he eats one? Everybody. 100 newtons for 10 seconds is what Ryan pushed in the back of the car. Or I can back up my other car, right? And I can do this. Done it for a second. Not too hard, again. Right? You make sure you touch the bumpers. There's a whole bunch of collision stuff you don't want to get involved with, right? Oh, yeah. Guys, I used to drive old cars. I've towed my car home many times, all right? I'm so happy I have a job now where I can pay an auto mechanic to fix my problems. All right. Everybody, I want you to see that these two are equivalent. You guys agree these are both the same value for the delta P? All right. Force and time, therefore, are directly proportional to the impulse, which is the change in momentum. All right? Oof, stuff. Is that a mouthful? Right? And again, we can do a problem, but the thing to realize is this is Newton's second law. All right? And the way the book says it is that this is what Newton discovered, guys, for the second law. But we will simplify this. We don't need to know this. All right? Newton's second law can be simplified to this. And this is what chapter 5 is. And I know chapter 4, I don't know if it even shows in chapter 4. Okay? But this is Newton's second law. Because everybody, what's velocity divided by time? Acceleration. And acceleration is the agent of change on a mass, all right? And that's what causes us to make a force. Because again, velocity itself, all right, when you have a change in momentum, if you're going to have a change in momentum, let's talk about this. Think about it. I have a car on the road, and it's rolling along, and it has momentum, but there's no force. But all of a sudden, you run into a tree. Why is there force? Because the momentum changes. But what happens when you crash into a tree, unfortunately? You keep going. Listen, your car deaccelerates from 50 miles an hour to 0 miles an hour within a 2-foot crunch zone. Guess what happens to you? Unfortunately, you wait another millisecond of time, and then you deaccelerate from 50 miles an hour to 0 when you hit the steering wheel. Or go through the windshield. All right? But I guess here's my point. Everybody, there's an acceleration there. We were going 50 miles an hour. We hit a tree and we're going 10. I got hit about a year ago. I was pulling out from a stop sign. Someone behind me wanted me to go faster, I guess. Because I was pulling out at about 5 miles an hour and they rear-ended me. All right? The acceleration there wasn't as bad because you're kidding me. Oh, that's not our belt. Because my acceleration, I had some velocity at least, all right? The person hit me hard enough that I accelerated. I was going 10 miles an hour. She bumped me, and I was going 14.
Thanks.
Exactly. Pull over, make sure everybody's okay, and we drove on. It wasn't a big deal, but acceleration again. There's a change in the velocity, and if there's a change in velocity, you have acceleration, guys. And acceleration causes force. All right. So force equals ma. So when we start getting ready to break bridges, which is still out there, all right? Force equals ma. Acceleration times the mass of an object equals a force. That's why when Tim's running down the hall, I'm a little nervous about him running into me. And when a kindergartner's running down the hall, I'm a little nervous about them getting hurt. All right? And it's why when Tim's behind the wheel, I'm really scared about what he's doing. Because, guys, he has increased his mass and his acceleration 20-fold. All right, everybody? And the force you can generate when you get that type of mass around you is very high. All right, it's all about direction of force, right? Yep, you're still moving forward. Yep, you're still velocity, you're just going forward. Yep.
So you hit a deer.
Okay, so when you hit a deer,
It's like you're driving, if you see a deer and you just decide
to hit them full speed.
Is that different?
Officer Foster, Zach Bennett to the office, please. Officer
Absolutely.
Foster, Zach Bennett, would you please report to the office?
I mean, listen, the amount of, think about this, the amount you de-accelerate there. All right?
So for that, would you use would you use the acceleration and the direction that, what would you do?
Talk about the deer.
You start with deer.
Well,
Deer's running forward.
all right, listen, now you're getting to some very complex engineering problems because, listen, no, seriously,
Like a car.
it's a deer in a car, but listen, you're talking about whether you tromp it or whether you skid to a stop to slow down for it.
Assuming we did it at full speed.
All right. Listen, do you agree that the mass of the deer is constant?
Yeah.
And no matter, and the question is, what kind of splatter we get? All right. So there's two ways to do it. So Tim, if I slam on the brakes, right, and I see a deer, 'cause that's what normal people do, like me. All right, and I'm slowing down. The second I hit the deer is going to impart at that instant some change in velocity, right? So I'm skidding, 60, 50, 40. I can't miss it. I hit him at 40. You guys agree that at the second you're crushing the deer, you might go from 40 to 38. All right? Because you hit the deer and it skids through, right? That's your change in momentum, everybody. So your deceleration, that instant, the force the deer puts in is based on that A. Okay? Here's the
What
thing.
is the A? That's
Yeah.
what we're saying.
Oh, the A would be a deceleration, right? I was going 40 miles an hour.
Yeah.
Sure thing. Well, it depends which.
Why?
I'm decelerating.
Negative force.
What's the difference in the force per direction, guys? If I have a negative force, what's it mean? It just acts opposite direction. So if I'm accelerating this way, which way is the force going against me? When I hit the deer, it's going opposite. All right? And again, signs of these numbers simply indicate a direction. Now let's be clear about this. I hit the deer, let's pretend 2 meters per second, it weighed a couple hundred, so 500 Newton force into my bumper. When I hit the deer, I put 500 Newton of force into the deer. What's the deer do? And that takes us, boy, I can't even believe I led into this so well. That takes the Newton's third law. For every force, all right, there is an equal and opposite force that's the same. All right, so Tim, you accelerate. You're just going to put more force in the deer. I'm taking 500 Newtons. You're hitting 700. And guys, it's not the initial hit, right, with deer. The crush zone. We're pretending that the car is one of these big steel boxes because what happens when you really hit a deer? Everything starts caving in. Do we agree? Cars have been designed so the force won't get transferred, right? It accepts a collision here. In this type of collision, the force goes into the auto body, right? And when you take it in there, that's called a collision, and that's all kinds of stuff. We're going to pretend that force is transferred straight up. Very good. Very good. These are elastic and inelastic. We will stick to inelastic because they're easy to calculate. So when you hit the deer, Tim, in our little world, your car has no damage. You transfer it all into the deer, and the deer transfers all to you, and you get up and you drive away. Welcome to physics. All right? But listen, we also know that we can calculate those forces. And this is the problem you guys didn't like in the homework. Mr. Anderson's going to tow home his car that doesn't work.
Yeah, that's why.
Here's Mr. A's car. Tim's going to haul me home. All right? So I hook up the chain. Tim's a smart guy. He knows to keep tension on it. And he has to pull me. And he's
Yeah, there's that.
And he's going to pull me with 1 kilonewton of force to make my car roll. Everybody, if I have to be pulled with 1 kilonewton of force this way to get momentum, what is pulling against Tim's car? 1 kilonewton of force back, right? He's pulling me, and that's what's causing the motion, all right? And what he feels to back his car is a drag. 1,000 ample, equal and opposite. And when you do, if you want to know what Tim's car is feeling, I break this. Did I cut? What's the one thing I cut when I drew my red circle? The cable, all right? Yep, the machine here. And if I draw this again, this is called a free body diagram now. What force am I seeing? 1 kilonewton. When I draw the other circle, for my car, what do I see? Same 1 kilonewton. All right? Equal and opposite. So, just bear with me. This will take some practice for. We're talking about track pilot. But picture you and I holding the rope. I don't have one. I should. I toss out a rope, and you and I each pull with 10 pounds. Which way are you pulling with 10 pounds? You're pulling towards Mr. Pickett. Which way is Mr. Anderson pulling with 10 pounds? Equal and. Now in the real world, we and I have a tug of war. All right. If we stand still, 200 pounds, we lean into it. Still equal and opposite. Of course, I'm stronger, better athlete, jump higher, all this stuff. So eventually I start pulling you this way. Now we don't have an equal and opposite situation. We don't have a static situation. Do you agree if I start pulling you this way, your velocity was 0, and your velocity goes this way? What do you have to go from 0 velocity to velocity this way? Force, acceleration, which goes to a force. Right on. Everybody catch this? If the motion accelerates, you have force. Once Tim starts pulling you guys at 2 miles per hour, and there's no acceleration, there's no force. And what happens? This is when bad things happen, right? All of a sudden the cable gets a little slack. Oh yeah, and then you get the old. Wow, I need to better change that. They don't break. I just until you break the bumper off.
Yeah.
So everybody, it comes down to equal and opposite force. Newton's 3 laws. We will not. We cannot destroy energy. When we put energy into a system, it has to go somewhere. If Tim hits a deer, the energy that's lost from this collision goes into the deer mostly. You guys agree? It is almost typically for sure the loser of the battle. Right? We do not destroy energy. All right. So the question becomes then, why don't you coast down the highway at 50 miles an hour? Friction. And on the road, from the air, guys, we're not just, when you burn a fossil fuel, all right, you're making energy. That energy turns into motion, and the friction is what's equal and opposite. All right? Yeah, in a car, fossil fuel. We ignored that part of it, all right? Because that is, again, initially we just got to be able to balance the system. Is everybody with me? Forces will come out of nowhere. We create, but when there are equal and opposite reactions every time we do this.
Well,
Yeah.
that's why I guess I did a country different. There's pulling you out of the ditch or it's like okay, well, I guess if he's pulling you winning you like you're winning you
Okay. Oh, initially.
confused by your picture.
All right. As Tim accelerates me, there's a force. Both of us will have a force. If Tim is accelerating us both out of ditch from 0, he might have a force of 2 kilonewtons, but he's still pulling me with 2 kilonewtons. All right.
You're pulling.
I might need 1 kilonewton worth of pull just to go a certain velocity. I see where you're going. Okay. But another kilonewton, that last kilonewton would do what to my system? It would make me go faster. You agree, Corey? And if I have acceleration, I have force, okay? We'll work on it. All right. But I guess 3 rules. An object in motion wants to stay in motion, an object at rest wants to stay at rest. Everybody agree with that? All right, F equals ma. Force equals mass times acceleration. That's Newton's second law. And Newton's third law is for every reaction, there is an equal and opposite reaction. Is everybody with me on those 3 laws? The only equations then for this whole chapter to really break it down to that is F equals ma is obviously really important. It's Newton's second law. Is everybody with me? And momentum is mass times velocity because mass matters. When would these problems get very, very, very hard? Can you think of it? Can you think of a situation where these problems get really hard? When the mass is changing. Guys, how about shooting a rocket? Let's talk NASA. Listen, shooting a rocket in space is really hard because how do they get into space, everybody? They've got to overcome gravitation by burning fuel. Does anybody know what the fuel is? Rocket fuel. Mostly liquid oxygen, isn't it?
Yeah.
Mostly. I mean, you can.
Well, other, like, solid.
Yeah, there's other things too, right? But here's the thing: as you burn those boosters, whatever the fuel is, what happens? We don't have that physical force. A force goes down, and we lose mass. And guess what? You think these equations are hard? Now, P equals mass times velocity. Our mass and our situations are always the same. The good news is I won't make you launch rockets. We'll kill deer. And does the mass of the deer and the mass of the car ever change?
Well, unless parts fly off the car.
Let's parts fly off the car of the deer, but that's after the collision. So the initial point of contact when force is transferred, that instant, the deer's mass and the car's mass are the same. Yeah, but that's a whole new problem. That is now elastic collision or an inelastic collision, and you have to have a transfer of forces. And again, you might say, where does the force go? When you start breaking bones on the deer, that's where the force goes. When you start scattering the innards, outers, that's where the force goes. All right? Like I planned these lessons. Like Glenn Mrs. Davis left because she saw the best part of the whole 45 minutes. You gotta agree.
Yeah, you got to transition.
I really did. Everybody, force equals ma. Force equals ma, and we're gonna start practicing free body diagrams. The other thing we're gonna work out Wednesday. I'll give you the worksheet. This is not due till next Monday. We will work out Wednesday. You should look at it. If this is super hard for you, you probably need to study. If it's super easy, I probably will give you an option Wednesday. You can either work with us on this worksheet, or you can do it ahead of time and do something else during the class period, all right?
On Wednesday?
Not Wednesday, but tomorrow we're going to set the move, all right? Take a look at this. You might have time to look at it tomorrow, all right?
Sandbag. Oh, there, okay. Sandbag.
All right. Trying to think if I got anything else. We will move to chapter 5. And we'll talk about static and dynamic on Wednesday. Hey, and next week, I should have scheduled lists for each day. I think that's pretty much what we expect. We'll talk about that tomorrow at the booth. What did I say? Don't whine in my house. That's the only rule.
What?
Great.
Huh?
Don't whine.
Don't whine. I hate.
If you look at things that's so you might want to have kids. A lot of kids whine.
I would.
I just make it fun of my kids. Don't whine. Well, no. What am you?
Yeah. Younger child.
All right, tell you what, guys, you can go a minute early. Got some early lunch today. Listen, student council meeting tomorrow during homeroom. Student council during homeroom tomorrow. Probably Mrs. Sands' room. My room will be filled with math students panicking with the semester ending.
It's funny because they don't.
It's funny because it's true.
panic about.
I don't know.
off.